This video clip will describe and show comprehensive ways of performing meta-analysis in STATA and also performing subgroup meta-analysis when the outcome is continuous and binary, and how to calculate the effect size, which can be based on standardized mean difference for a continuous outcome, or a odds ratio or a risk ratio for a binary outcome, and how to produce forest plot and funnel plot in STATA. If this video is useful, subscribe to the channel and leave any comments or queries regarding the video in the comment section, and click on the notification bell to receive the most recent releases of video clip to the channel, and click on the like icon and share the video with others, so that the channel can develop and improvise to include further wide scope of different statistical method and how to perform statistical techniques in several different statistical packages such as SPSS, Excel, STATA, Jamovi, R statistics, GraphPad Prism, G-Power, GMP, and revaman. Meta-analysis to draw a forest plot and funnel plot in STATA. Meta-analysis is a statistical method that combines the result of two or more studies to estimate a pool effect size. The meta-analysis or the statistics method will measure also variability, degree of variability or heterogeneity among the results by producing an overall confidence interval, 95% confidence interval, and a value for I-squared test, which is a homogeneity test, and the I-squared value is expressed in percentage, and high value of heterogeneity indicates that the result of individual studies may be too different to combine, and a low value of the percentage indicates no heterogeneity, i.e. homogeneity. Forest plot is a graph representing the result from the meta-analysis. It does summarize the overall effect size estimates, and it gives a 95% confidence interval for multiple studies, and also it displays the magnitude and the direction of the effect size, and also it identifies sources of heterogeneity or inconsistency in the results. The forest plot diagram or plot consists of three main sections or part. The first part is a statistical analysis for each study with 95% confidence interval, p-value, probability value, and an estimate effect. The second part is a diagram with estimate and confidence interval 95%, and the third part is the overall statistical analysis of the effect size and the test of heterogeneity among studies. Funnel plot will assess the publication bias in meta-analysis. Here in STATA data view, I had inserted 10 studies or data from 10 studies, study number 1 to study number 10 as shown here for the column or the variable study, with a year publication for each study given in a bracket. And then next to that is the treatment. So here we have two groups. The study is arranged into two groups: treatment or experimental group and a control group. So T stands for treatment and N stands for the number of participants or cases in each study for the treatment, and the mean is given for the variable continuous, as the variable is here a scale, and then a standard deviation for the treatment is given also. And for the control group, the number of cases for the control is given, and the mean for the control and the standard deviation for the control. So for each study there is a mean, sample size and standard deviation for the control and for the treatments. And the objective of meta-analysis is to combine the result from all these 10 studies to finally reach a conclusion whether there is effect size difference between the treated group compared to the control. To do meta-analysis in STATA with a data that is continuous, in the window here click on statistics, scroll down to down until you reach the meta-analysis section, click on it, then a new window will appear for meta-analysis control panel. There are several sections here: setup, summary, forest plot, heterogeneity, publication bias for funnel plot. So for the current studies here, we need to declare the meta-analysis data. Since we have the data as a continuous outcome, not as a binary outcome, then we will compute and declare the effect size for the two groups, the control and the treatment, for comparison for a continuous outcomes. So if the data was binary, then we will stick with the binary. We'll select the first option. And if we scroll down here, as we see in the main section, specify group 1, which is treatment variable, and specify group 2, which is control variable. So the sample size for the treatment is the Tn, for the mean is the mean T, and for the standard deviation is SDT. And for the control, the sample size is N control, mean is mean C, and standard deviation is standard C. For specifying the effect size, there are several options. If we click on the option here, options are given whether to go for Hedges G, Cohen D, Glass delta and Glass delta 2 and 1, and mean differences. We'll select the Hedges G. Click on submit to declare the meta-analysis data. And as shown here in the window, the command for the meta-analysis is meta-e estimate size, and these are the parameters: the number of cases, the mean, the standard deviation for control and treatment. Number of study is 10. Study size is meta study size, and these are the summary data, and the effect size is Hedges G, and precision is given by given a confidence interval which is 95% level, and the model selected here is a random effects. If we want to modify the meta setting, then click on that, and then certain modification can be done, but we will leave it as it is. For clicking on the summary here, keep the meta-analyzed model declared model, click on submit, and then and again, as shown here, a table is generated for each study from study number 1 to study number 10, and Hedges for each study is calculated, the estimate size, and the 95% confidence interval for that value is given, and a percentage of weight is also given here with a probability value. To generate a forest plot, click on submit, and then a forest plot will be generated as shown here. The forest plot will have 3 sections: the statistical analysis for each data with the descriptive here, and here is the statistical analysis, and then the graph representation, and in the third section is the overall size effect and the heterogeneity test. To do editing for the plot section here, in the option for the plot options, click on the plot options and tick on draw overall effect size line, and then line options, and let's give the line a color red and make it dash here rather than solid. And if you click on accept, and then for a line of no effect, tick on that, then select an option, then tick on line option, and then select the blue color and select the dashed pattern. Click on OK, click on OK, and then resubmit again. Another graph modified plot, forest plot, is generated. From this plot, on the left hand side is the descriptive stat for the 10 studies with the number of cases, the mean, the standard deviation for the treatment or the experimental group, and for the control group. And in the middle is the graph representation. On the right hand side is the Hedges, which is given here, value Hedges G 1.14 for the first study, and 1.42 for the study number 10, and then confidence interval 95% confidence interval for the estimate effect is given also for each study, and a weight percentage of the weight also given, and the weight percentage represent or reflect the size of the study. If more participant or larger study size will have a higher weight influence, as shown here for the 16%. So each study is weighted based mainly on its size or the number of participants recruited for the study. Looking at the plot here, Since the effect size is a scale and it's continuous, the variable is continuous, then there is a value of 0, and it can be 0, 1, 2, and it can be also in the minus. The blue dotted line is the line of no effect, i.e. when the differences between the control and the treatment effect size is equal to 0, which means there is no difference, so they are equal. And the red dotted line is the overall effect size, i.e. the Hedges G, which is given here 0.73 from pooled or combined 10 study, and it is represented in a green diamond. So the location of that represent the overall effect size, and for each study the effect size, which is Hedges value, is represented by a square, as shown here, a blue square, and the size of the square reflects the sample size or the weight. So higher studies with higher number of participants will have a higher weight, and it will have a larger blue square, and the center of that square will represent the effect size or the Hedges G value, and the horizontal line for each study will represent the 95% confidence interval. And as shown here, most of the studies are very approximate or close to the overall calculated effect size. Looking at the third section in this plot, which is the heterogeneity, specifically the I square, and the value for it is 22.2%, which this indicates that there is low variability between the studies, and the p-value for that is 0.28, not significant, which indicates that there is a homogeneity between the studies. And finally, the overall effect size, as the data is standardized, so Z value is given here and a p-value less than 0.05, so there is a significant difference. So from this study, it shows that combining all the 10 studies, there is a common shared observed conclusion that there is a difference between the treatment group compared to the control group, and the overall size effect is significant. So thus there is a genuine significance between the treatment and the control, and seems to be that the control have an effect. Moving away from the forest plot and continue with the form here, if we click on heterogeneity, again this is an option to select from. We'll leave it as it is, and then click on submit, and a graph is generated here for the Galbraith plot. But what is interesting is the publication bias will generate a funnel plot. So we will use and select the funnel plot for graphical diagnosis of a small study effect, and then click on submit. Funnel plot is generated as shown here, with the y-axis is standardized error, and on the x-axis is the Hedges value, and as shown here the Hedges value is about 0.7, and the red line represent that overall effect size, and these, each one of these circles represent the one of the 10 studies. And for lack of bias, all the studies Hedges or effect size should be distributed evenly across this red line under the funnel. And we see here 1 2 3 4 5, 1 2 3 4, so there are 4 in the last on the right side, 5 on the left side, and 1 outside the funnel plot. Meta-analysis in STATA when the outcome is binary and the estimated effect size is an odds ratio. Meta-analysis will be performed to generate a forest plot and funnel plot. Here in this STATA data view, I had placed 12 studies taken from literature for 12 publications that addresses or investigate a specific or the same scientific question. So in each study, individuals were recruited into the study and the participants were segregated into two groups, control group and treatment group or intervention group. And the treatment group were given a drug and followed up to see whether the condition is treated, and a control group which is also being given a placebo or no treatment, and the condition were observed whether the condition has been reverted back to normal or the individual recovered. So here from these variables or small data set, it shows there are a variable for study ID from study 1 to study 12, and then the sectioning of the intervention group, which is the treatment group for T. When the drug was successful, the number of the patient that recovered from the condition were counted, and the number of the individual did not recover were also counted. So here we have data for a treatment group for those who successfully recovered and those who failed to recover. The second section here is for the control group, in which the individual who were successfully recovered from the condition without the treatment were counted, and those who did not recover and failed to recover from the condition were also recorded. So here we have two groups, and we want to compare the effect of the drug on the recovery of the condition. So we are looking at association between the taking the drug and recovery from the disease. And since the outcome here is binary or binomial, whether successful or failure, so either yes or no, so whether successful or failure, so this is a nominal outcome, and it has only two levels in it, successful or failure. To find out the association, then an odds ratio will be calculated. And to perform meta-analysis for these 12 studies, comparing them and pooling them and summarizing the result from these 12 studies to reach eventually a conclusion whether there is an effect of taking the drug on treating the condition, then meta-analysis will give the pooled effect size based on the odds ratio. To perform the meta-analysis, in the section here for the STATA, click on statistics, scroll down to the option which is for meta-analysis, click on it, a new window will appear which shows here the meta-analysis control panel window. There are several sections for the meta-analysis method, and these sections need to be filled. Setup section, summary, forest plot, heterogeneity, regression, publication, bias, and multivariate. So we're going to select and fill some of these, as the focus will be on generating forest plot and funnel plot. The first step is to declare that the data we have is a meta-analysis data. And since we are computing a binary outcome, then click on compute and declare effect size or sizes for two groups comparing or comparisons of a binary outcome. So we have here a binary outcomes that have two levels in it, or dichotomous outcome. So once this is selected, scroll down here and in the main section enter the variables for, first of all, the specified group 1 and group 2 as shown here. The groups are sectioned and labeled as treatment variable, control variable. So the number of success, tick on that and then select for success, and the number of failure for the treatment, select the treatment failure, and for the second group, which is the control, select the C for control success and C for failure for number of failure. And to specify which effect size to use, there are several options, whether to go for odds ratio or risk ratio or risk differences or logo peto's odds ratio. So stick to the log odds ratio, and then to declare the data, click on submit, and as shown here, the data is identified as for meta-analysis to perform the meta-analysis, and a 95% confidence interval will be generated, and a random effect model will be selected, and the method selected is the RML. Once the form is submitted, we could also go back again and modify setting if we want. For the model here, we could select the random effects or fixed effects. We'll stick to the random effects, and then the models we could use is as shown here. There are several options. If we are interested in the fixed model, then the Mantel-Haenszel's method can be used, but let's stick to the random effects, and we've already submitted that. Moving to the second section here, which is the summary. Again, another window will appear, and as we said here, summarize meta-analysis data. We've selected the random effect. We stick to the restricted maximum likelihood. We could click on RE options. We are not going to do sensitivity test. We stick with the basic here. Since we are not interested in doing subgroup meta-analysis, this is a section if there will be a subgroup meta-analysis. If we take on options for the confidence interval 95, report effect size, we say report just the effect size without exponentiated. We stick with that. So let's click here to report a t-test and z-test for overall effect size. And let's take and see what is in the display options for setting up the coefficient decimal format. None of interest. Then if we click also in maximization, no options will be selected. Once we have filled this form, click on submit to submit the conditions or criteria, and as shown here, a table is generated for the meta-analysis summary and shows that from study 1 to study 12, the odds ratio is generated for each study with 95% confidence interval and percent of weight. The weights reflect here impact of the sample size on the analysis. And as shown here, a probability value is given, and Q value is given, and also for test of homogeneity, for Q value and a P value. Continue with filling the forms here, or the sections. If we tick on the forest plot and then select the random effect, keep everything as it is. If we click on options here, again there are certain options here to select from. We could also report t-test instead of z-test for the overall effect size. In fact, I'm going to stick with the z-test, so I'm going back again to the summary and untick this and then submit that again. So we have here similarity in both selection. And for maximization, no changes. For forest plot, few changes here. For options to change the confidence interval bracket, whether bracket or parentheses or none. I'm going to do a few modification on the plot. I'm going to select to draw the overall effect size line, and by giving this, also clicking on line options and giving it a color of, let's say, blue. And if we find here the blue, and then pattern, let's say the pattern is dash, and then click on accept. For the no effect line drawing, click on options and line options, and then let's give it a red color, and then default, let's make it a pattern for dash, and then accept, and then okay, and then okay again, and ignoring the rest here. And for test options, no changes here. And for two-way options, no changes here. So now we are ready to submit the form. If we click on submit, a diagram is generated, which is the forest plot. So the forest plot here has three sections: the descriptive statistics, the diagram here, and the overall statistical analysis. And as shown here on the left hand side, the study ID from 1 to 12 and descriptive statistics for the intervention and the control, and the number of those who were cured and not cured, as shown here. On the right hand section, the odds ratio is calculated and given here for each individual studies, from study number 1 and to study number 12, and then 95% confidence interval is given, also calculated and assigned next to the odds ratio, and the percentage weight for each individual study is given here, that should all adds up to 100%. And as shown here, the overall odds ratio is given, which is 2.79 with a confidence interval. The next section in the graph is the symbols here, that each one of them represent each study. The small square represent, blue small square represent the estimated effect size, with in this case, which is the odds ratio. So the odds ratio for the first study is given in a square here, and it's 3.8. So it's around here, 3.8, around this area here. And the horizontal line represent the limits for the 95% confidence interval for the upper and lower limits. And as shown here, the size of the square, or the estimate size, effect size is variable, or the sizes are variable. So some squares are larger and some squares are smaller. The size of the square reflects the weight percentage. So higher number of participants will have a larger square. The blue vertical line is the line representing the overall or the pooled odds ratio, which is 2.79. And the red dashed line is the line of no effect, and as shown here there is a ruler or a scale for the odds ratio. Moving to the third section in the forest plot, shows the overall test for homogeneity and overall effect size. For homogeneity test, tau squared is generated. We will stick to the I squared value, which is equal to 12.1%, which shows low level of heterogeneity, and p-value of less than 0.05 will make it more heterogeneous. But here, since the value for the p-value is greater than 0.05, so this will indicate that there is a low level of heterogeneity. So for low level of heterogeneity, the p-value should be higher. So this meta-analysis showed that there is low level of heterogeneity, for which is around 12%, and a p-value of 0.4. For the overall effect size, which is the overall odds ratio calculated here, which is 2.79, this odd ratio is significant, statistically significant, as the p-value is less than 0.05. And from that meta-analysis, it is fairly could suggest that the analysis would suggest that intervention by using this drug have an impact and an effect, and it can improve the recovery from the condition, as the odds ratio for those who were treated is 2.79 times more than those who were not treated. So the drug is effective. So that is the essence of performing meta-analysis on these 12 studies to finally reach a conclusion that they all looks like they are all agreeing that there is an influence of taking the drug, or the drug is associated with the recovery. This is the way to analyze the forest plot. Back again to the forms here for meta-analysis. We've already submitted that and we draw the things. Let's move to the section for heterogeneity. Again, select the random effects, and there will be no much changes here. Just click on submit. A graph is generated, which is the Galbraith plot. Will not describe it here. We'll move to regression. No major selection of a regression at this stage to do. The most important thing is to look at publication bias. And the way to look at publication bias is to draw funnel plot or do another regression, which is called Eager's regression. What are we going to look for? Publication bias, funnel plot for graphical diagnosis of a small study, test for small study effect in meta-analysis. We'll stick with the funnel plot, and the main thing is a standard funnel plot, nothing in FN, and model. Select the random model options. As shown here, we could specify the y-axis metrics using standard error, inverse of standard error, variance, inverse of variance, sample size, or inverse of sample size. Stick with the standard error. And there are certain things here we can select: reduce separate plot, pi group, suppress meta setting information, not of interest. Let's go and click on submit, and a funnel plot graph is generated as shown here on the y-axis. standard error is given, and on the x-axis is the effect size, which is the odds ratio for each individual study, and these dots represent each individual studies. The plot here is in the shape of a funnel, inverted funnel, and the red line is the overall effect size or pooled effect size, which is 2.79, and the dot, as I explained, each one of these dots is the estimate size for each individual study. For no presence of publication bias, the distribution of the estimate effect size on both sides of the funnel should be equal. So here there are 1, 2, 3, 4, 5, 6, 7 above the estimate effect size and 5 below. So here there in this plot indicate that there is a certain bias in the publication, and further test ought to be done. Meta-analysis for a binary outcome based on an effect size, which is risk ratio in STATA, and generating a forest plot and a funnel plot. A binary outcome is a variable or a data that have two levels in it or two categories. An example is the status of live or life or dead, does have a disease or doesn't have the disease, smoking is not smoking. So the data are in only two levels, so it is binary or binomial, and sometimes it's also called dichotomous. And the risk ratio is the ratio of the probability of an event occurring in a intervention or treatment or exposure group compared to the probability of the same event happening in a control or unexposed or reference group. Here in this STATA view, I had inserted 12 studies, data extracted from 12 independent studies that addresses the same scientific, medical, or clinical question. Each study was designed to have two groups. Participants were allocated either to the exposed group or to the reference group, which is the control group. So the exposed is treatment and the control is the reference group, and the number of events occurring in the exposed group is reported and scored and inserted here, and the total number for participant in that group of exposure is also inserted, and a number of no event occurring in the exposed group is also recorded. So the number of event occurring in the exposed group is recorded, and the number of event occurring or happening in the control group is also recorded, and the total number for each participant in each group is also given here. Since the outcome here is binary, as there is only an event happening or an event not happening, so there are only two levels, yes or no, then meta-analysis for a binary outcome will be performed, and the estimate effect size that will be generated here or calculated is the risk ratio. And the way to do that in STATA is to back again to the section command here, and then click on the statistics, scroll down to the section or the options that says meta-analysis, click on the meta-analysis option or stats, and a new window will appear as shown here. This is the control panel. This is the window to perform and select and enter the data required to perform meta-analysis. And to perform the meta-analysis, first we have to declare the data here in this setup, and to choose the right and appropriate effect size based on the outcome. Since the outcome is binary, then select the for the setup, compute and declare effect sizes for two group comparison of a binary outcome. In our case will be the risk ratio. And for the main here, for the first group, which is the intervention group or the treatment, and for the second group we need to fill these empty areas. So the number of success, which is the number of event happening, which is the T event. Number of failure is the number of no event happening in the first group, which is the treatment group. For the second group, which is the control group, number of success happening is the control event, and number of failure is control no event happening. So here two groups, event occurring, no events for the intervention or treatment or exposure, and for the reference the same, event happening, event not happening. For the specific effect size, there are several options, and we are going to use here the log risk ratio as we're going to use this effect size. If we click on a model, I'm going to select here the random model, and for the method there are several methods, but we'll stick with the restricted maximum likelihood method. Click on options, no selection in this part, and if we click on submit, we'll notice that the data is declared for meta-analysis, and there are, as shown here in the summary, 12 studies. Meta-analysis will be performed. The data or the variables are the first group, which is the intervention, event no event, control event no event, and the effect size is the log risk ratio, and 95% confidence interval will be calculated, and the model used, which is a random effect or effects model, and the method is RML. If we click on the next option here or selection, again summarize the meta-analysis data, click on the random effect model, use the random effect models. In the options, no changes. In the maximization, no changes, and then click on submit. And as shown here in the submit option, a meta-analysis summary is generated with an I-squared given here in a percentage, which is 21.28%, and a random effect model and a method given, and for each study a risk ratio is calculated with a 95% confidence interval and a percentage of a weight, and the percentage of a weight indicates or reflects the size of the sample. So a larger sample will have larger weights, and that will have an influence in the meta-analysis calculations. And as shown here, a heterogeneity test is performed based in the Q statistics, which is based on the chi-square, and a p-value is generated which is greater than 0.05. Back again to the window here. To generate a forest plot, again click on the forest plot and then click on random effects, and for other options no selection will be taken. Click on options here, no selection. For maximization, no selection. For forest plot, what I'm going to select here is the plot options, and I'm going to tick for the draw overall effect size line, and then click on the line option, and then let's give it a blue color. If we select the pattern, we'll go for dashed and click on accept. And for draw no line of no effect line, click on options, click line options, make it let's say red, and this is the red, and make it dashed, and then click on accept, click on OK, click on OK again, and click on submit, and that will generate a forest plot. As shown here in this forest plot, there are three sections. The first section is the descriptive statistics, the second one is the diagrammatic representation, and the third one is the overall heterogeneity test, and also overall estimate of the effect size. As shown here, the studies are numbered from 1 to 12, and there are two groups here for each study: intervention and control. Yes for event, no for event not happening, for both groups. And here on the right hand side, the risk ratio has been calculated for each individual study, and a 95% confidence interval is also produced, and a weight percentage is given for each individual study. The diagrammatic presentation here in the middle is a reflection of the descriptive data. The squares here represent the effect size, which is the risk ratio for each individual study. Higher or larger squares reflects larger weight percentage or larger sample size. The horizontal line here represent the 95% confidence interval, lower and upper limit. The blue line here represent the overall effect size, which is the overall calculated risk ratio. In our case here, it is 0.85. And the red dashed line here represent the line of no effect. So this is the diagrammatic representation. The third section in the forest plot shows that overall estimate of the effect size risk ratio, which is 0.85 with a 95% confidence interval. Heterogeneity test with an I-squared value generated and a p-value. And as shown here, there are 21.2% variation among the results here, and we need the p-value here to be higher than 0.05. So there is low level of heterogeneity among the results from all these 12 studies. The last section here shows that the p-value is less than 0.05, which means that the risk ratio or the overall or pooled risk ratio is significant. So from this meta-analysis forest plot, a conclusion can be drawn about the overall risk ratio for these several studies that answering a specific medical question. From the meta-analysis also a funnel plot can be generated. Back again to the section here to fill. If we click on the heterogeneity, no selection will be considered. For regression, no selection, but for publication bias, I'm going to select a plot drawing, which is the funnel plot, to check for publication bias. There are several options. We'll select the first one, and no selection for the models or the model, no selection for the options. For the model, in fact, I'm going to stick with the random effect. For options, no selection. For graph options, I will not perform any changes here. And if we click on submit, a plot is generated in the shape of a funnel. On the x-axis is the risk ratio or the log risk ratio, and on the y-axis is the standard error. And the red line in the middle is the pooled overall risk ratio, which was 0.85. And the circles here represent each individual risk ratio for each individual studies. So here we have 1, 2, 3, 4, 5, 6, 7, 8 studies on the right hand side, and 4 and 3 studies on the left hand side of the red line, and 1 outside the funnel. For publication bias, for lack of publication bias, the distribution of the risk ratio should be equal on both sides of the line. So there should be same number of risk ratio studies with risk ratio above the line and below the line. And here we have 8 above the line and 3 below it, and 1 outside the funnel. So this indicates there is publication bias. Further test is required to validate this observation, which is the Eggers regression test. Subgroup meta-analysis with a binary outcome and an effect size, which is the risk ratio in STATA, to plot forest and funnel plots. What is a meta-analysis and subgroup meta-analysis? Meta-analysis is a statistical method that combines data extracted from several independent research studies, whether these studies are clinical or medical or healthcare. The objective of meta-analysis is pooling the data and determining the overall estimate of the effect size. In this case is the risk ratio in a intervention group relative to the control group, those studies that addresses the same scientific, medical research or clinical question. Subgroup meta-analysis is a meta-analysis in which the studies or the data in the studies are separated or segregated based on a variable or a characteristic, such as the gender of participant, male or females, or the ethnicity of the participant, and so on. So the meta-analysis will split the studies based on a variable or a factor, for example the gender, males or females. Then it will pool the data for the males and the females and calculate the overall effect size for males and females, and then compare the outcome for the pooled overall effect size for males and females. Here in STATA data view, I had inserted a data taken from 12 studies, clinical studies numbered from 1 to 12 with a label of study ID. Each study had recruited participants and grouped them into a intervention group or treatment group and into a control group, and the number of events occurring in the exposed group is recorded here, and in the control group also recorded. For the event occurring for the event no occurring, not occurring in the exposed, and event occurring in the control, and event not occurring in the control, with a total number for each group. So there are here several variables describing the events happening in each study, and the objective of the study is to compare the relative risk between the exposed group and the control group. Here on the far right hand side is the a factor or a variable or a characteristic variable, which is gender, whether have a male or a females, and as shown here, 6 of the studies only recruited males, and the next 6 had recruited females. Here the outcome, or the recorded or the measured outcome, is binary, as the outcome or the variable have only 2 levels in it, either the event occurring or not occurring, so it is binary or binomial. And to perform meta-analysis on the data here extracted based on the risk ratio, and also in fact doing we could do here 2 type of meta-analysis, either binary meta-analysis for the 12 studies, or subgroup perform subgroup meta-analysis for the male and the females, and then compare the outcome or the output for both. And the way to do subgroup meta-analysis in STATA, in the section here for the command, and on the top click on statistics, scroll down until you find an options or a statistical function, which is a meta-analysis. Click on that, then a new window will appear, or a form to fill for the meta-analysis. There are several sections here. We will fill some of them, not all of them, as the interest here is to perform subgroup meta-analysis. And the first step here is to declare what type of data and what type of meta-analysis to perform. And since our outcome is binary, then we will compute and declare the effect size, which is the risk ratio for 2 groups comparison of binary outcome. Once this is ticked, then in the next section here, 2 groups, the first group, the second group, the exposure group, and the control group, and here fill it with the number of success, which is the T success, and number of failure, which is T failure. So this is event happening, this is no event. And the same thing for the control. The control will be C success for an event occurring, and C failure for the event is not occurring. And for specifying effect size, select the log risk ratio, as we are going here to use the effect or calculate the effect size based on the risk ratio. We could also click on the model here, and we can select whether it is a random effect or common effect or fixed effect. And if we are going to select random effect, then the method, there are several methods that can be selected. Restricted maximum likelihood, Hedges, Hunter-Schmidt. We'll stick with the first one. And for the options here, we could also add the study label, which is the study ID, and the label for the effect size, which is the RR, which is the risk ratio. So here we had filled most of the section for the setup. If we click on submit, then as shown here in the output for the STATA, there were 12 studies and the label for these studies are study ID, and the study size is meta study size, and the input variable or event is the T event occurring in the in the treatment, no event in the control, no event in the control, and the label is risk ratio, and a 95% confidence interval will be produced, and the model chosen are the random effects, and it is RML method. If we move again here into this section and click on summary, this is very important as we need to perform subgroup meta-analysis and stick to the random effect models. Click on the subgroup meta-analysis and choose the factor you want to segregate or split the analysis based on the gender here, which is the 6. So we need to produce, in fact, 2 separate meta-analyses, one for the male and one for the females. If we click on options again, no changes to be taken here. Maximization, no changes. If I click on submit, again a few tables are generated in STATA window here, and as shown here, the table for the group male and the table for group females, 6 studies, and the risk ratio for each individual study is calculated with a 95% confidence interval with the percentage of a weight, and the same for the females, and also an overall or pooled risk ratio for the males is calculated, and for the females also calculated with 95% confidence interval. And the overall, without doing segregation, without doing subgroup meta-analysis, risk ratio is calculated. So here for just meta-analysis, here for subgroup meta-analysis for the male and for the females. And in the next section here, it's also produced a heterogeneity summary for the male and the females, and as shown here, the heterogeneity test is based on the Q statistics, which is based on the chi-square, and the value is generated, and an I-squared is given here with a percentage and a p-value. And as shown here for the males group, there is no heterogeneity. All the results are homogeneous, and the p-value is greater than 0.05. We need the p-value to be higher than 0.05. For the females, however, the I-squared, there was a high percentage of heterogeneity for the females group, as it was 41.4, and the p-value was greater than 0.05. And also a heterogeneity for the overall. This is an overall heterogeneity test for the meta-analysis, and this is for subgroup meta-analysis. And as shown here, for the complete meta-analysis, is the I-squared is 21.5, and the p-value is greater than 0.05. So there is low level of heterogeneity for the overall meta-analysis. Back again to the form here, to click on the forest plot. So we need to generate a forest plot, and again select the random effect model, and for the subgroup we need to generate a forest plot that has 2 sections in it, one for the male group, one for the females group. Then select the subgroup meta-analysis factor, which is the gender. For the options here, if I tick in it, I'm not going to perform any changes. For maximization, no changes. But for the forest plot, I'm going to click on the plot options, and I'm going to select the draw overall effect size line, and click on line options, and I'm going to let's say label that in a red color, and choose a pattern of let's say dash, but let's make it long dash here, and click on accept. And for the draw no effect line, again click on it, click on options, and then line options, and then let's change the color to select blue, and then let's make it dash here. Click on accept, click on OK, and then click on OK again, and I think we are ready to hit the submit icon here. And as shown here, forest plot is generated, and there are two sections, one for male, one for females. This in fact is sub-meta-analysis, a forest plot for sub-meta-analysis. And as shown here, there is a section for the males, females, and then overall for the meta-analysis without segregation. As shown here in the plot, it is made up of three sections: the descriptive statistics, the diagrammatic representation of the descriptive statistics, and the third section, which is the overall calculation for the heterogeneity and the pooled effect size. For the first section here, which is the subgroup meta-analysis for the males, the study label is given from 1 to 6, and the number of events, which is labeled here as yes, for the treatment group is given, and for control group is given, and also the number of no events. And in the far right hand section here is also the risk ratio for each individual study is calculated and inserted as shown here, with a 95% confidence interval and a weight percentage. A weight percentage reflects the sample size which will be included in the calculation and will have an impact or influence the overall meta-analysis, and this represent higher weight percentage, represent higher participant in the studies. So this is again repeated for each individual studies for the male and the female or both sections. And under each section or subgroup, heterogeneity is calculated for the male group with an I squared which is equal to 0% and a p-value greater than 0.05. So there is no heterogeneity among the results, and also a p-value for the overall effect size. So here also an overall risk ratio is calculated, which is 1.74. The same thing for the females. And as shown here in the second section of the plot, which is a diagrammatic representation, a square represents the risk ratio for each individual studies. There is variation in the size. Some squares are larger, some are small. This reflects the size of the sample or participants, number of participants in the study. Larger squares have larger number of participants and larger weight percentage. The horizontal line here is the 95% confidence interval, lower and upper limit, and the diamond shaped symbol here is the overall risk ratio for the male subgroup. And the red dashed line is the line for not the subgroup meta-analysis, but for the meta-analysis overall risk ratio, which is given here. And for the blue line is the line of no effect. Now here we have the descriptive statistics for the male and the same for females, with the risk ratio calculated for each individual study, and overall risk ratio for the male and for the females. As shown here, the risk ratio is 1.74 for males and 1.49 for females. So there is a differences between males and females, and that's the essence of performing subgroup meta-analysis, to find out and compare the groups, subgroups, and to find whether there is a differences. And again, for the females, the I-squared value is given, which is 41.4, and the p-value is given here for the heterogeneity test, and the p-value for the overall estimate effect size. And again, we can see from both that this overall risk ratio for males and females is statistically significant, as the p-value is less than 0.05, and the risk ratio fit within the 95% confidence interval. The final section here, which is an overall for the meta-analysis rather than subgroup meta-analysis, and it's shown here. If we perform meta-analysis without grouping, then the I-squared will be 21.5%, and the p-value is greater than 0.05, and the estimated or calculated effect size, which is the risk ratio, is 1.56 with a p-value which is significant. And also here, as it shows that it's also test for group differences. So from this forest plot, overall risk ratio for males is calculated, overall risk ratio for females is calculated. This is for the subgroup meta-analysis, and for the just meta-analysis, an overall risk ratio is also calculated. So the objective of drawing the forest plot from either meta-analysis or subgroup meta-analysis to draw a conclusion based on the risk ratio, and to compare the finding between sections or subgroups of the data. In addition to the forest plot generated, a funnel plot can be also produced to test for bias in publication. I'm going to skip the clicking for heterogeneity or regression, and I'm going to click on the publication bias, and I'm going to select the options for how to test the publication bias based on funnel plot for graphical diagnostic of small studies effect. We could perform some test here, or we can perform the third option, and I'm going to stick with the standard funnel plot. And for the models, we're going to stick with the random, and for the options, no major changes will be done here, but we could stick on produce a separate plot by group, and we select the gender factor. The STATA will generate two plots, one for the male and one for the female. So plotting the funnel plot is based on the gender factor, and if I click on submit, here a funnel plot or plots has been generated from the subgroup meta-analysis, one for male and one for females. We could do a overall funnel plot without segregation, but here we look at the funnel plot for the males and the females. On the x-axis is the risk ratio for each individual study, and on the y-axis is the standard error. So this is a scatter plot with a funnel shaped, and the red line in the middle is the overall risk ratio for the male and for the females. And for lack of publication bias, the distribution of the effect size, which is the risk ratio from the studies, has to be evenly distributed above and below this red line. So if we look here at the female section, we can see, or female funnel plot, we can see here we have 1, 2, 3 on the right hand side, 1, 2, 3 on the left hand side. So there we can say here that there is lack of publication bias for the female section, as the distribution of the effect size or the risk ratio is evenly, or there is a symmetry in the distribution. For the male section here, as we can see, two effect size or two risk ratio from the studies, which is 1, 2, 3, 4, 5, 6, 2 above the line and 1 below the line and 3 on the line. So further analysis need to be done here to confirm the publication bias, such as Eager's regression test need to be performed. If we are interested in doing funnel plot without segregation, back again to the form and untick the produce separate plot by group and click on submit. A funnel plot will be generated for the meta-analysis or binary meta-analysis without segregation, and as shown here, without considering the sex of individual, male or females. Here we can see that overall there is bias in publication, as here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 studies on the right hand section and 3 on the left hand section. So there is no symmetry in distribution of the effect size, which for each individual study. So there is a bias in publication. There is a bias in publication for the overall, and this also again need to be confirmed by Eager's regression test. If you are an undergraduate or a postgraduate or even a researcher and you have the data and you want to analyze that data in any of these packages, statistical packages, such as SPSS, STATA, Jamovi, R Statistics, GraphPad Prism, GMP or revaman, then contact me to arrange a one-to-one private tutor session, or if you are interested in joining a training course for performing statistical analysis using any one of these listed packages, then do contact me on the following email address to arrange for either a private tutor session or a training course for several weeks.